The simplex method is an iterative algorithm that moves from corner to corner until it reaches the optimal solution. Imagine the following was the feasible region for an optimization problem where you were trying to maximize the function 2x plus 3y. We'll use this example to visualize how the simplex method moves from corner to corner. We could evaluate each corner and then just choose the largest evaluation amongst all the corners to see that the corner 4, 5 will be the optimal solution where the optimal value is 23. The simplex method starts at any corner. It identifies its neighboring corners, those that share an edge, and then moves to the corner that has the highest evaluation. It repeats this process until it's on a corner that has no neighboring corners that are better. For feasible regions constructed by linear inequalities, this method will always terminate at the correct solution. Here, if we start at 0, 0, we have two corners. There are two edges. One evaluates to 11, the other 8. Because 11 is larger, we'd move to that corner. In the two-dimensional case, we can only go forward or backward along these edges, and it would make sense that we would always move forward. If we started at a different corner, we could do the same process, identify the neighbors, and move to the neighbor that evaluates larger. Identify the two neighbors, move to the neighbor that identifies the larger. Here, regardless of where we'll start, we'll end up at the corner 4, 5, which evaluates to 23. For linear programming problems with 3 variables, we can still visualize what's going on. Here, the feasible region takes on a 3-dimensional shape. We can imagine that this figure is the feasible region for some set of inequalities. Given some objective function here to maximize 2x minus y plus z, we could go and evaluate each of these corners. Again, here we could just directly read off that the optimal solution is x equals 4, y equals 0, z equals 3, and the optimal value is 11. We can visualize how the simplex method moves from corner to corner. If we were to start at the origin, we would identify all the neighboring corners. We could move to 0, 0, 1, 3, 0, 0, or 0, 2, 0. Here, the corner that evaluates to the highest value is 3, 0, 0. At this point, we would check what are the neighboring corners. There's 4, 0, 3, 4, 3, 0, or go back to 0, 0, 1. Here, the one that has the highest evaluation is 4, 0, 3, and we could move to it. Here, the simplex method continues because the simplex method doesn't know that this is the best one. It would check the 3 corners, 0, 1, 2, 0, 0, 1, 4, 4, 4, and it would see that it's already on the best one, and so it would terminate at the corner 4, 0, 3. Starting at a different corner, we might have a different path that we traverse. Between the 3 neighboring corners, 4, 3, 0 is the next best corner if we were to start at 0, 2, 0. At 4, 3, 0, its 3 neighbors evaluate to -2, 6, and 8. It would move to the corner that evaluated to 8, which is 4, 4, 4. Here, this corner 4, 4, 4 checks its neighboring corners and would move to the 4, 0, 3. Again, because the simplex method doesn't know that it's at the optimal solution yet, it runs one more check and sees that it's at the highest of all its neighbors, and it correctly concludes that it's at the optimal solution for the system. The benefits of the simplex method is that it continues to work for higher and higher dimensions. Even though we might not be able to have the same methods of visualizing what's going on, the generalized form of what it's doing, starting at one corner and moving to the next best one at each step, it will end up on the correct optimal solution.